All right, we're on. Good. You're back with me here. And let's just go ahead and set up the slideshow for this guy. All right, what we're going to be talking about here is spherical mirrors. Okay, spherical mirrors. And there's two kinds of mirrors. In other words, we're going to pretend that a mirror is a sphere on both sides. Okay, so we're going to take a mirror that is a sphere. It's hard to say. It's like rural juror. From 30 Rock. But anyway, so we're going to take this mirror that's spherical, and it's either going to, and we're going to turn this side, we're going to pretend like we're on the inside here, and this would be a concave mirror because this is the reflective part, and notice it's curved this way. So this is like if you're looking at a spoon and you're looking at the inside of a spoon, all right? And then if you turn it around, then you've got a convex mirror, okay? Then this is called convex. Concave, it caves in from where, and here's the center of curvature is what this is called, the center of curvature, or the radius of curvature right here. We'll call this C. And then we'll talk about focal length, the axis, all that kind of stuff. All right, so now we're talking about mirrors because we've talked about total internal reflection, we've talked about index of refraction, and now we're going to talk about mirrors. All right, so again, this is the way light behaves like a particle. Now remember, we've already talked about flat mirrors. So any reflection that we're going to see in a concave mirror, if it's behind here, that's going to be a virtual image if it shows up behind you. But actually with these kinds of mirrors, with a convex mirror, you're always going to get a virtual image, and it's always going to be upright, and it's always going to be shrunk. All right, so yeah, that's the thing that I do with you all. I usually start with the notes, the note part. Okay, so let's just let me do some freewheeling here, and let's go to the ladybug. I should have had him turned on already because sometimes he's a little tricky to turn on, or he'll just shut off inexplicably at times. Okay, so that's good, and I kind of like the big screen. I don't know if you liked it or not. I don't like having that ladybug dot right there. I don't know how to get rid of it, but there we go. That's a good thing. Here's my bear. That's what you keep seeing up here. This is my bear. It actually was my dad's bear, but when I inherited, I don't know why. I was just cleaning out his apartment in the assisted living where he's living before he passed a couple of years ago, and I was like, I like that bear. He got it while he's on a trip in Michigan with my mother. Oh man. All right, so anyway, so that's what you see every once in a while in the corner. There's the bear. All right, so let's look at mirrors, and let's get the definitions down. Concave mirror looks like this. This is concave, where the radius of axis is here, and then the reflections are coming off here. Now remember, so if you got a straight light wave coming in, it's going to, angle of incidence is going to equal the angle of refraction, so they're going to come in like this. Like that. All right, so that's concave. Convex mirror looks like this. Another good way to do this, this is perfect. So a spoon. All right, so this is the concave side. All right, convex side, concave side. Right? And you can play little mind games with these spoons too. It's a lot of fun. Wow, I'm inverted. Inverted, upright. Inverted, up. As I spin it and I look at my reflection, I don't know what you can see, but anyway, okay, I'm upside down. Turn it around this way, I'm right side up. Whoa, cool. All right, we're going to talk about all that. Convex mirror. And here are the terms that we're going to be radius of curvature. That's C. Radius of curvature, we use as C. And that's like for a concave mirror. It's like, remember, this is a circle, it's a sphere. So this is a circle. And so this R goes R. We always use capital R. Big R, big R. Those are all the same. I didn't draw it very well, but those are all the same. Radius of curvature is C. Okay? And focal length. Focal length is a physical property of a spherical mirror, and the focal length is equal to the radius of curvature divided by 2. Radius of curvature will be r, right? But they show it as c in the slide. You know, the point is c, but they call it r. It's radius of curvature. Focal length is radius of curvature divided by 2. We've got a distance of the object, do, distance of object. Di, drill instructor, no, distance of image. Sometimes, now we're not going to do double lenses or anything like that when we get up to the lenses. We're going to do mirrors first, and then we'll do lenses. The distance of the image, sometimes it's negative for mirrors and for lenses. All right. Distance of the object will always be positive for our purposes. Sometimes it will be negative, especially if you're doing double lens things, like figuring out the equations for telescopes, microscopes, those kinds of things. All right? Okay. And I'm trying to think, oh, and magnification. Is magnification. So if something has a magnification of negative 400, that means it's not negative 400. If m equals negative 400, that means it's upside down, or what we call inverted, which means upside down, and huge. And that would be huge because it's 400 times bigger than, taller than what it really is. Just, but the image of it is upside down, right? So that's magnification. And then, of course, there's the height of the object and the height of the image. Height of the object. Height of image. All right. And we use all of these to get our big equations here. And here they are. And then we'll work through the slides here in a second. But here's what we're talking. So magnification, of course, is equal to the height of the image divided by the height of the object. It's also equal to the negative, and I put in parentheses, of the distance of the image divided by the distance of the object. Okay. All right. And here we go. We know that F is equal to R divided by 2. Now here's how we do, here is our mirror equation. It's only one equation. It's really cool. We've got this guy, but here's the mirror equation. Look at this. It is so much fun. 1 over the focal length, and don't convert unless you have to. Unless we're talking about like a movie projector where the distance between the object, which is the film going through there, and the lens of the camera and the screen that's projected on, which might be, that distance might be centimeters apart, and then the screen is like a couple meters away. Then you'd want to convert, I'd convert to centimeters. Conversion's usually not necessary. I'm just setting down the ground rules. Conversions, not necessary. Okay, and I better wrap this up. Once I write this lens equation, I'm going to write this is equal to 1 over do plus 1 over di. And then the rest is just manipulating these 3 things right here based on what we see. All right, so there's your intro into mirrors. All right.